Hello, everyone. Thank you so much for being with us tonight in our in-house audience here at Burlington House on Zoom and on YouTube. Hello, my name is Lucinda Offer. I'm the Education and Outreach and Events Officer here at the Royal Astronomical Society. And it's my pleasure to welcome you to tonight's RAS Public Talk in March. Tonight we have with us Dr. Marie van de Zande, our 2023 Caroline Herschel Prize Lectureship winner, which was established in 2018 by what is now the Herschel Society in association with us, the Royal Astronomical Society, to celebrate Caroline's memory by supporting promising women astronomers early in their careers. And Dr. van de Sande is also an Oort Fellow at Leiden Observatory at Leiden University in the Netherlands, and she studies the chemistry around dying sun-like stars by developing novel chemical models and comparing the results to observations. Mary obtained her PhD in 2018 from KU Leuven in Belgium, where she stayed on as a fellow of the Research Foundation Flanders. She moved to the University of Leeds as a Mary Sklodowska-Curie Individual Fellow in 2021 and relocated to Leiden in September 2023. And we're very happy to have her back here in London today for this event. Please welcome Dr. Mary van de Sande.
All right, thank you very much for, let me first see if I can change slides. Wonderful. Thank you very much for the introduction, Lucinda. I'm very happy to be here, the Royal Astronomical Society. It's really an honor to be here since I published a few papers with the monthly notice of the RAS, so now I'm here. That's quite, very cool. But I'm especially very privileged to be here to talk to you about the relatively new, exciting research field of astrochemistry, and also how it's linked to Caroline Herschel's research. Because it's quite a long talk, I'll first start with an overview. So I'll begin with just general astrochemistry. We'll then move on to the astrochemistry of dying stars, which is my research field. And then finally, we'll hop onto the dust produced by these dying stars and see how it gets us to like life on Earth and planets. So when you think about astronomy, you maybe think about very big things, such as these, there's so many enormous stars out there that make our sun look like only just a tiny marble. Maybe you're thinking of very extreme environments, such as neutron stars, which are about the size of the Earth, but contain twice the mass of the sun. So very extreme environments that are all out there in space. Maybe you're thinking on much larger scales. Maybe you're thinking outside of the Milky Way, thinking of different galaxies and clusters of galaxies and how they interact. But if we want to really understand the intricacies of a galaxy and to understand where we come from, we need to look at much smaller scales. And by small, I mean very small. I'm talking about atoms and molecules. And to begin with a bit of a history lesson, during the Big Bang, only hydrogen, helium, and a little bit of lithium was formed. Everything else, the carbon in our bodies, the oxygen in the air, all the heavy metals in the projector and the computers, was all forged in the hot cores of stars that died a long time ago. And when they died, they expelled their life's work back into the universe, and somehow we ended up with this configuration, our Earth and us on it. And exactly how stars and planets are formed, and very likely also how life is formed, is all encoded in the chemistry of galaxies. And that's exactly what astrochemistry is all about. So astrochemistry is the study of molecules, and not just which molecules are where. It's also about their formation and destruction mechanisms, so which chemical reactions produce or destroy specific molecules. And by doing so, we want to find out how they influence the structure, dynamics, and evolution of astronomical objects. So that's a very broad definition that covers a very broad range of topics and environments. And that's, well, precisely the point. Astrochemistry is very widely applicable. And throughout the life cycle of a galaxy, we can distinguish several astrochemical laboratories. So this is a depiction of the life cycle of a galaxy. Stars are formed from clouds of material that occupy the space in between the stars. This is called the interstellar medium, or the ISM. And then the life and death of a star all depends on its initial mass, or which you can look at as its birth rate. So if stars have at least, well, 8 times or more the mass of the sun, they will die in a very violent supernova explosion, expelling all of their life's work back into the interstellar medium, all in one go, one big bang, not the big bang, but like a pretty big bang. And the only thing that's left behind is a neutron star or a black hole. And that again depends on the initial mass of the star. Stars like our sun also die, but they do so in a much more gentle, controlled manner. So rather than throwing everything out all in one go, they lose their outer layers in a more gentle way by means of a stellar outflow. And at the end, the only thing that will be left behind is a white dwarf. So as stars die, they expel all the heavy elements produced in their cores back into the interstellar medium, where it then forms the building blocks for the next generation of stars and planets. So a bit like reincarnation, but more of a cumulative reincarnation, if you will. And astrochemistry can tell us all about, well, can tell us more about the different stages within the life cycle of a galaxy. Right, the first molecules were detected not too long ago. So astrochemistry is quite a young research field. So the first molecules were detected in the 1940s, so not even a century ago. And there were these very simple molecules, CN, so the cyanide radical, CH, and also CH minus, so that CH with an extra electron added to it. And they were discovered in the interstellar medium, in the very tenuous regions of the interstellar medium. And the discovery came as a big surprise to both astronomers as well as chemists, because you wouldn't really expect molecules to be present within the, well, space. Because space is a very hostile environment if you're a molecule. You've got 2 main issues. You've got density and the UV radiation. Let's start with the first one, density. So these molecules were detected in a region where the density lies around 10 to 100 particles per cubic centimeter. And that's not a lot at all, especially when you compare it to the air in this room, where we got 10 to the power 19 particles per cubic centimeter. So 10 to 100 is really, it's not nothing, because there's something over there, but it's nothing compared for almost a complete vacuum to us. Now, to form a molecule, you need at least 2 atoms colliding with each other and forming molecular bonds. But at such low densities, that can take quite some time. In fact, it can take a couple of centuries before 2 atoms meet each other to form a molecule. So that takes a very long time. But fortunately, time is on our side. If you're an atom in such a diffuse cloud, you spend roughly a few thousand to 10,000 years. So while it might take a few centuries before you meet somebody else, you've got time, you can wait, you can form a molecule. But then you have the other issue, that of ultraviolet radiation. And I think we've all experienced the various effects of UV radiation here on Earth, which is a sunburn. So every year I still get a sunburn, even though the sun doesn't emit doesn't emit a lot of its energy in the UV at all. And we're also protected by a very thick atmosphere that filters out most of the UV radiation anyway. And still, people get sunburned. Now, if you are a molecule in space, you are not protected by a very thick atmosphere because, well, you're in the interstellar medium. And what's more, you're surrounded by a bunch of different stars. There's a bunch of suns, but there's also a bunch of massive stars, which really just blast UV radiation in your general direction. And the molecular equivalent of having a sunburn is photodissociation. So UV photon hits a molecule and it falls apart back into its atomic constituents. So you've waited around for centuries to finally meet another atom to form a molecule with, and then it only takes 1 photon for you to be broken apart again. So it's a very hostile environment, but still we find that molecules are present somehow within this region. And astrochemistry really took off in the 1960s when radar equipment left over from the Second World War was repurposed as radio telescopes. So rather than looking at the enemy, we just pointed up towards the sky and loads of new molecules were found. So in this graph, you see the number of detected molecules over time. So in the 1940s, we've got a few. In the 1960s, we see that the number of molecules really shoots up. And as technology continues to improve, this slope becomes steeper and steeper. The two main astrochemical observatories at the moment are ALMA. So ALMA is the Atacama Large Submillimeter Array. It's an array of 66 radio telescopes located in the Atacama Desert in Chile. So it's 66 radio telescopes collaborating together and acting like it's one huge telescope. And then, of course, you also have the recently launched James Webb Space Telescope, which is shedding new light on the universe, well, infrared light on the universe. Right, so this is a recent census of the all of the molecules detected so far, divided by the number of atoms over here. So you see so in total, there's roughly some 300 different types of molecules that have been detected, and most of them are quite simple, so 2 to 3 atoms. The most abundant molecule is H2, the hydrogen molecule, simply because, well, about 75% of all matter is hydrogen. You've also got things that we know, such as carbon monoxide, loads of water floating around. And you see that the number of detected molecules decreases as we go up in number of atoms, but as our technology continues to improve, we're really filling up this space as well. So you've got lots of molecules that you already know about, but you also have quite funky molecules floating around, such as HC3N. So that's 3 carbon atoms in a row, topped off with 1 hydrogen at one end and a nitrogen at the other end. If HC3N were to walk into this room, it would be hydrogenated in no time, since the density in this room is quite large. There's also lots of water. And look at all these beautiful unpaired electrons. It's just asking to be reacted with. But in space, the conditions are just so that you can make quite a bit of HC3M. You can also do that here on Earth, but it takes quite a lot of effort, and you need a special lab for it as well. The most complex molecule detected so far is C60, or a buckyball. So that's 60 carbon atoms arranged in a spherical shape. That's a very stable structure. So you might wonder why we go through all this effort of detecting molecules, because, well, telescopes are expensive and time on a telescope is expensive. And we do this because molecules are very sensitive probes to the physics of the environment in which they're found. For example, for something like HC3N to exist, you know that you need a certain density. It can't be 10 to 100. It needs to be a bit higher, because you've got 4 more atoms involved. They need to be, they need to have found each other at some point. You also know that the UV radiation field shouldn't be too large, because otherwise it would have broken apart again. So detecting different molecules tells you a lot about physics. So chemistry really helps to constrain the physics of your environment, and that's very valuable when you want to pin down the structure, the evolution, and the dynamics of these environments. Right, oh, again, slide change. Okay, so that's enough about astrochemistry in general. I will now take us on a journey along the life cycle of a galaxy and following the chemistry along the way. And why not start at the end? Let's start with the astrochemistry of dying stars. So we are back with this life cycle. So I mentioned before that the life and death of a star all depends on its initial mass. Massive stars, so more than 8 times the mass of our sun, as they run out of hydrogen in their core, they will swell up and become a red supergiant, so several hundred times the size of the sun. A famous example of a red supergiant is Betelgeuse in the constellation of Orion. Betelgeuse is the bright red guy over there. It's very easily observed by the naked eye, maybe not in the center of London, but surely in the outskirts you can quite easily find Orion and detect Betelgeuse. Now, after the red supergiant phase, gravity finally wins and the star can't withstand its own gravity anymore. It starts to collapse into it. Oops, oh my God, I'm collapsing myself. It starts to collapse into itself, and as a result, it will explode as a supernova. So all of its outer layers are ejected all in one go back into the ISM. There's a few famous supernovae. So you've got one that went off in 1987. So supernova 1987A. It's quite a famous one because it's the first supernova that we were able to study with modern astronomical means. So there's entire conferences about this object. The thing that's left behind from the massive star is a neutron star. Another nice remnant is the Crab Nebula. So that's a remnant of a supernova that went off in 1054, which was documented by Chinese astronomers at the time. And at the center here, we have a pulsar, which is also a neutron star, but a highly magnetized one that's also rotating. And if these stars would have been a bit more massive, they might have become a black hole. So supernova is all very exciting and it really speaks to the imagination, but only a minority of stars ends its life in that way. Most stars are stars like our sun, and they die a much more gentle death. So as the sun runs out of hydrogen in its core, it will also start to swell up, but rather than become a red supergiant, it will become a red giant. So just a few 10 times its size rather than a few 100 times its size. And then after this red giant phase, it will also lose its outer layers, but in a more controlled way by means of a stellar wind rather than an explosion. And the only thing that will be left behind is a white dwarf. And for a very brief period of time, just some 10,000 years, it will be able to light up all the material that has just been lost and form a planetary nebula. Now, the mass-losing phase occurs during the AGB, or asymptotic giant branch phase. And that's a very descriptive term if you're an astronomer, but admittedly, it's not the best for PR purposes. Like supernova does have a better ring to it, but this is a very important phase nonetheless. And here you see an AGB star in all its glory. So this is IRC 10216, also known as CW Leo. It's an image taken in the optical by the Hubble Space Telescope, and you see all this material moving away from the star. The outflow is quite a large object, so in this image it spans about 2,000 astronomical units, and an astronomical unit is the average distance between the Sun and the Earth. Now, keeping in mind that our solar system is just 100 AU, this really is an enormous object. Now, in fact, you can't see IRC 10216 itself because it's hidden behind all of the material that it's expelling. More specifically, it's hidden behind all of the dust that is being formed within the outflow. And that's really something quite special because forming dust means you have a phase transition. You go from the gas phase to the solid state, and it's quite difficult to do, especially in space. And the outflows of AGB stars are one of the few environments where you can efficiently produce a lot of dust. So these AGB stars are very efficient dust factories. And through their outflows, they pollute the interstellar medium or chemically enrich it. This is another example of an AGB star. Now we have got Myra. This is an image taken in the UV. Myra itself is somewhere over here on the right, and it's moving, it's losing its outer layer, so blowing a little bubble, but it's also moving through space, leaving this tail of material behind. And in total, the tail of material spans some 13 light years. So here we see an AGB star caught in the act of polluting, chemically enriching the environment. So let's dive a bit more into the chemistry of these outflows because they're very rich astrochemical laboratories. They host different types of chemistry, including the elusive dust for condensation of dust. So here is a very simplistic cartoon of an AGB star on the left. Now, the chemistry of your outflow is all determined by the elemental carbon to oxygen ratio of your star. And this is because of the strong molecular bond of the carbon monoxide molecule. If you put carbon and oxygen together, it really wants to form carbon monoxide. It really wants to form CO. So if you have a C/O ratio smaller than 1, you have more oxygen than carbon. You can then assume that most of your carbon is locked up into CO. So the thing that's left behind is oxygen. You will have an oxygen-rich outflow. Now, all stars start out as oxygen-rich. But during the AGB phase, there's a process happening called a dredge-up. And that's a very descriptive term because during a dredge-up, material is dredged up from the core. So freshly formed carbon is dredged up up to the stellar surface. So with each dredge up, you've got more and more carbon at the surface of your star. And after a while, you will have a C/O ratio that's larger than 1. So now you've got more carbon and oxygen, you will hence have a carbon-rich outflow. Now, our sun will never become a carbon-rich AGB star because its mass isn't big enough. It will not be able to go through enough dredge ups to become carbon-rich. So the chemistry of your outflow depends on both the star's age and the initial mass. Not all stars will become carbon-rich. Right. The AGB star itself is not very nicely behaved. The outer layers are convective, so it's like a huge pot of water boiling over. And this is a simulation of such an AGB star. So you see these huge convective bubbles pushing material out that then falls back onto the star and then up and down again, like a huge pot of boiling water. And these convective motions cause shocks, which bring the chemistry close to the star out of equilibrium. So close to the star, in the inner wind, we've got non-equilibrium chemistry. Then a bit further out, the density is still high enough, but the temperature is low enough for dust to condense from the gas phase. And I mentioned before that this is really quite special. You've got this phase transition from gas phase to the solid state. And the type of dust that's being produced depends on your C/O ratio of the star. If you've got an oxygen-rich star, you will form metal oxides and silicates, so tiny sand grains. If you've got a carbon-rich star, you will produce lots of amorphous carbon, which is basically soot. These carbon-rich outflows are large combustion engines in a way. And this dust is very important to the evolution of your star, because the dust is opaque to the infrared radiation of your star, which means that once one of these infrared photons hits the dust grain, the photon's momentum is absorbed by the dust, and it starts to accelerate away from the star. And as it accelerates away from the star, it bumps into the gas, drags it along, and launches an outflow. So it's the formation of dust that really launches your dust-driven wind. So it's a chemical process of dust formation that determines the further evolution of your star. Since the outflow is quite strong, and it's not the nucleosynthesis in the center of the star that determines the end of its life anymore, it's really the outflow itself. And then finally, we reach the outer regions of our outflow, where the material reaches its terminal velocity, which lies between 5 to maybe 30 kilometers per second, which isn't too fast in astronomical terms. And the chemistry in this region is a very rich photochemistry, since UV photons from our interstellar radiation field, which is just like the sum of all the stars that surround you, are able to reach this region and make a very reactive soup of atoms, molecules, and ions. So we've got 3 different regimes of chemistry all within one object. And this is largely because of it being an outflow, which creates these enormous gradients in density and temperature. So close to the star in the inner regions, we've got densities of about 10 to the power 13 particles per cubic centimeter and temperatures of a few thousand Kelvin. And this decreases to some 10 particles per cubic centimeter and some 10 Kelvin, where the outflow merges with the ISM. So these are very large gradients, and it's because of these gradients that we've got such a rich astrochemical environment. Now, you might expect that if you have a spherically symmetric star, you would create a spherically symmetric outflow, but of course, nothing is quite as easy as it seems. So we've got quite some cool observations. For example, here you have the outflow around R Sculptoris. This is CO emission as observed by ALMA. And you see that there's a spiral present throughout the outflow. That's not very spherically symmetric. Another nice example is L2 Puppis. So this is an image taken by the SPHERE instrument on the Very Large Telescope, also in Chile. And the dark band that you see here is actually a dusty disk that hides whatever's going on from our view. And these 2 cones of light is light that's being scattered off the dusty disk. Now, there's also ALMA observations of this star, and they seem to suggest that there's a massive planet within this disk, a planet roughly about a Jupiter mass in size, and if you were to scale it back to, bring it back to our solar system, it would be roughly at the orbit of Uranus. Now, L2 Puppis used to be very similar to the Sun, used to have the same initial mass, one solar mass. And well, we also have a massive planet in our outskirts. So perhaps L2 Puppis is what's in store for our solar system in the future in a few billion years. This might be a glimpse of that. Now, as observations continue to go on, it's becoming clear that spherically symmetric outflows are the exception rather than the rule. So these are some 12 oxygen-rich HGB outflows. The red is, again, emission in CO. The red is moving away from us. The blue is coming towards us. And none of these outflows are spherically symmetric, some a bit more so than others. So these ones are just a bit of shells, that's all right. But here you've got a bipolar structure. This is some sort of a space rose. And this guy has both a disk and a spiral, so it's really a mess. And we think that these intricate structures are caused by binary interaction, because most stars are actually not single stars. Our sun is quite unique in that aspect. Most stars have at least one or multiple stellar companions. And if you don't have a massive stellar companion, you might have a massive planetary companion, like Jupiter. And these companions have a large enough gravity to sort of pull the outflow into its orbit and create these intricate structures of spirals and disks. And this sort of links the AGB phase to the next phase in evolution, which is the planetary nebula phase. And these planetary nebulae have long been known to host such intricate structures. You've got a few spherically symmetric ones, a few nicely behaved ones, but you also have a lot of funky shapes. And it's been, has long been a question how you go from a spherically symmetric star with a spherically symmetric outflow to a thing like the red rectangle, which is a red rectangle. But maybe the origin of these intricate structures lies in the AGB phase, and perhaps it's being carved out by binary interaction. And planetary nebulae can be linked back to Caroline Herschel because she was tasked to look for nebulae. So nebulae are clouds of material that float around in the interstellar medium. And using some simple telescopes, she found quite a few of them, which proved to her brother William Herschel that if he uses his fancy telescopes, he would find many, many more. And this sort of spurred him on to create his famous catalogue of nebulae. But while they were looking for nebulae, William found a few strange ones, such as the Saturn Nebula, which he described as a curious nebula, or what else to call it, I do not know. These objects seem to be planets of the starry kind. Because you, of course, didn't know that he was looking at the final stages in the evolution of a star. He was looking at a dying star rather than a cloud of material. But he called it a planetary nebula, and we stuck to that term, and we still call them a planetary nebula. Right, so finally, we have reached the end of the life of our star. The star is dead, but this life cycle of the dust has only just begun. So all the dust that has been produced in the outflow is now entering the interstellar medium. And even though we don't know exactly how the dust is being formed, we do know that it plays a very important role to the physics and the chemistry of the interstellar medium, as well as to star and planet formation. So let's hop onto the dust and follow it into the interstellar medium, shall we? So most of the ISM is very tenuous, 10 to 100 particles per cubic centimeter, but you also have regions of higher density with 10,000 to 1,000,000 particles per cubic centimeter. And this is one of such regions. It's called a dark cloud, and I think it's quite clear why it's called a dark cloud. It looks like there's a hole in the sky, which might seem a bit concerning. But so in this dark cloud in particular will collapse sometime soon, in the next 1,000 years or so, and then it will become a stellar nursery. Loads of new stars will be formed within it, but so far it's just a dark cloud. Now, at these higher densities, we also have loads more dust grains. And these dust grains shield whatever's going on behind the cloud from our view. If we switch to a longer wavelength, to the infrared, we can sort of look behind the dust and we see that, oh, okay, great, there's loads of stars behind, everything's fine, there's no hole in the sky. So this really showcases one of the properties of dust, which is to shield against UV and visible light. And that's very important for the chemistry within this dark cloud, because the dust acts as sort of a sunblock and protects whatever chemistry is going on the inside from the ultraviolet radiation. So you can continue and react with each other without being too afraid of photodissociation. And it's because of this property of dust to shield against UV light that we can distinguish different types of chemistry throughout the ISM. In the tenuous region, in diffuse clouds, where we've got low densities, the chemistry is very simple. It's mostly atoms, some ions, and some very simple molecules, such as CN and CH, the first molecules that were detected. If we go to higher densities, we see that we can have more complex molecules. So we have water floating around, hydrogen cyanide, formaldehyde, but also funky molecules such as C4H. So 4 carbon atoms in a row, topped off with one hydrogen atom at the end. You wouldn't encounter that on Earth, and I think that's a good thing. It's probably very poisonous as well. So this really showcases how the dust is protecting these molecules so they can become a bit more well, they can contain more atoms. But we also find some actually complex molecules, some organic molecules, such as formic acid, which is what makes bee stings sting. You also have ethyl formate, which smells of raspberries and tastes of rum. And there's also a lot of methanol floating around. Methanol is the alcohol that will get you drunk, but it will also make you blind. So that's all floating around in space. And in fact, it's been detected at large abundances, so large amounts of these molecules that are too large to be explained with gas phase chemistry only. So gas phase chemistry is molecules and atoms floating around, bumping into each other. In order to explain the high abundances with which we see these complex organic molecules, we again have to turn to our friends, the dust grains, because the surface of the dust can act as sort of a meeting place for the molecules to find each other and react. And now I'm waiting for my little video to start. Okay, it works. The second time around, it went much faster. So here we have CO stuck to the grain surface, and the white dots are hydrogen atoms. They're very light, so they're efficiently, well, they're able to hop around the surface quite fast. While I'm speaking, we have methanol being formed on the surface of the dust. Hydrogen and CO keep arriving from the gas phase. So here we have HCO being formed, and they zoom around. And while these two molecules are much heavier, they can still move around, just much more slowly. And now we have methyl formate that was formed. Another carbon monoxide arrived from the gas phase. These two HCO radicals start to zoom towards each other and react. And now we patiently wait for a few more hydrogen atoms, and we have glycolaldehyde being formed. Wonderful. Another carbon monoxide arrives, and one of these hydrogen atoms finds it and makes HCO. And our UV photon knocks off a hydrogen atom from our methanol molecule, and these two radicals can come together and form another glycolaldehyde molecule. Now, this again takes a bit of time, but we have time. And over the span of a few 100,000 years, our dust grain becomes coated with an icy mantle of these complex organic molecules. And as our dust grain becomes part of a star-forming region, it gets warmed up. And as it's warmed up, it evaporates off all these complex organic molecules that have been formed on the surface. So these complex molecules were formed on the surface and then were evaporated off into the gas phase. And that's why we see them at such large abundances. So dust has two ways of helping chemistry: shielding against UV light and also providing a meeting space for atoms and molecules to meet and more efficiently react with each other. So as our cloud collapses, perhaps a supernova went off somewhere in the distance, giving its final push. Stars are being formed within this collapsing cloud, and this is an artist's impression of a protostar over here, surrounded by a disk of material that's falling onto the protostar. This disk is called a protoplanetary disk because this is where planets are being formed. And we now know that planet formation is a very natural byproduct of star formation. And the details of planet formation are still a bit vague in places, but we do know that it all starts out with dust, because you need two dust grains to stick together to form a larger dust grain, and then these stick together to form a little pebble, then you have a rock, then you have a planetesimal, and before you know it, you have a planetary system. Of course, before you know it, it's a bit more complicated than that, but it starts out with loads of dust grains. And these days, observations are as beautiful, maybe even more beautiful than artists' impressions. So these are a few protoplanetary disks as observed by ALMA. The emission that you see here is emission from the dust. So these disks all appear to have different shapes, but that's largely due to different orientations towards us. But you do see that some of them are smooth and some of them have these dark bands within them. And we think that these dark bands are gaps within the disk that are being carved out by planets forming within them. So what you have here is a planetary system in the making, sort of a 20-week scan of a planetary system. You can also take a look at different molecules within them. So here at the top, we've got the dust, and here in the bottom, in different colors, we have emission of different types of molecules. And by looking at the chemical composition of your disk, you can really pin down the process of planet formation, because you know more about the temperature and density, for example. But you can also start to, well, try to predict what type of planets are being formed within these disks. Maybe are they going to be gas giants? Are they like Jupiter? Are they going to be rocky planets like our Earth? It's all encrypted within the chemical composition of your disk. Now, the planetary system that we know the best is, of course, our own solar system. And this is a very zoomed out view of the our solar system. On the left, we have the sun. And on the right, we have our closest solar neighbor, or stellar neighbor, Alpha Centauri. Here we have all of the planets. But besides planets, we also have a lot of leftover material from when we were still within a disk. We've got an asteroid belt between Mars and Jupiter. Then you also have the Kuiper belt, which lies behind all of our stars. And surrounding it all, there's the Oort cloud. Now, sometimes some of these leftover materials hit the Earth. Most of the time, it's not a big deal when an asteroid impacts us. Sometimes all of the dinosaurs die, so it really is a bit of hit and miss. But you also have more benevolent visitors, namely comets. They originate from the Kuiper belt and the Oort cloud, so the more faraway regions. And they come by every, well, in this case, Halley's comet, every 70 odd years or so. Depends on the comet, of course. And these comets are, you can look at them as very pristine relics from the disk from which we are formed. So studying them is like studying an historical artifact. Now, Caroline Herschel discovered 8 comets. And this cartoon was published soon after she discovered the 3rd one. And it shows you a comet farting in her general direction. And the subscript says, what a curious smell, well, what a sulfuric smell this comet emanates. Well, oh, sorry, no, I forgot, I'll scroll down. What a strong sulfurous smell proceeds from the meteor. So very primitive humor, intended to make fun of Caroline for doing the very unladylike pursuit of astronomy. So fortunately, things are much better now. People aren't publishing any cartoons of AGB stars farting in my general direction when I publish a paper, or at least not that I know of. But yeah, that's what she discovered 8 comets, and people apparently weren't very happy about it. But let's talk a bit more about comets and less about farts. Studying these comets will tell us more about the disk from which we are formed, and that's why the European Space Agency sent the Rosetta mission to this particular comet, and in 2014 it reached its destination, 67 Churyumov-Gerasimenko 67b. And this is a picture of the nucleus of the comet. And you might have heard comets described as dirty snowballs. Well, that's not really a ball. That's more 2 things sticking against each other. So that already tells you something about how it was formed. And you can also see these like rays emanating from the surface. It's a bit better on the screens over there. And this is material that's being outgassed from the surface. So the comet is covered by all these ices, and as it comes closer to the sun, gets heated up and it sort of sublimates off these ices into the gas phase. Rosetta also took this sequence of images where you see a cliff over here, about some 20 to 30 meters high. So this is all the surface of your nucleus. You also have a bunch of rocks lying around on the surface. And lots of the stripes that you see here are cosmic rays hitting the detector, but the more fluffy bits is a bit like snow particles floating around on your comet. So here you have the geology as well as the weather on top of a comet, which is pretty cool. Now, Rosetta sniffed out all of the material that's being evaporated off this comet, and it found a real zoo of molecules. So this is just a list of all the molecules that were detected. You've got very smelly ones made out of sulfur. You've got all your carbon chains. You've got some alcohols, methanol, ethanol, all of them. You've got some very poisonous ones as well. But the king of the zoo is glycine, which is the simplest amino acid. And amino acids are proteins that are essential for life on Earth. So such a protein has been found on the surface of a comet, where it was formed purely by astrochemical means, astrochemical reactions. And this feeds into one of the theories surrounding the origin of life. We know that the early Earth experienced a heavy bombardment, loads of asteroids and comets hitting the surface, and they were covered with loads of ices. We know that most of the water came from these impacts, so water has an extraterrestrial origin, but maybe they were also covered with more complex molecules, maybe with like a bunch of glycine, some very simple sugars or fats, a bunch of organic molecules that could have really kick-started the process of life. So maybe like how planet formation is a byproduct of star formation, maybe life is sort of a chemical byproduct of planet formation if you're lucky enough. So when you think about formation of stars and planets, how we go from a dark cloud into a protostar surrounded by a protoplanetary disk, and finally with a star in a planetary system, when you think about all the chemistry that happens along the way and links the different stages, you shouldn't forget that it all starts with dying stars, expelling lots of heavy elements and loads of dust into the interstellar medium, providing the building blocks for this process to happen. And it's therefore very important to know exactly how stars die if you want to know how they're born as well. And astrochemistry is an important tool to understand this because it's the chemical process of dust formation that launches the outflow that sort of kills off most of the stars, all of the solar-like stars. So chemistry is important to know exactly how they die, how the outflow is being launched, but it also is important to the next stages of life, because if we know how dust is being formed, we know its composition, we know how large these dust grains are, and we can then follow the chemistry along the way. Now, I would like to point out that astrochemistry is not just observations. Of course, observations are very important. We need to know which molecules are where, but it also heavily relies on laboratory experiments. You need loads of spectroscopy in order to even be able to identify which molecules are in your beautiful observations. And then you also need lots of lab experiments to sort of figure out how fast or how slowly different types of reactions occur within the conditions of the ISM at very low densities, at very low temperatures. You need lots of, quite a few chemists handling machines like that in order to figure out reaction rates. And then there's a third component, which is theoretical models. So they take all the information from the laboratory experiments and make a sort of astrochemical environment in your computer. And by comparing your predictions to observations, you can then say something more about the physical environment and exactly what is going on. So astrochemistry really needs all three of them. They all rely on each other. So there's many different ways in which you can help answer the question of where do we come from? Right, and I'd like to end my talk with this slide. This is an image taken by the Voyager 1 mission on the Valentine's Day of 1990, right when it was about to leave the solar system. It looked behind itself looked back one last time and took this picture of the Earth. In case you can't see the Earth, it's this pixel over there. And this is really a group picture of all of humanity, because everybody who was alive or dead at the time is in this pixel. But also everybody who wasn't born yet is also in this picture, because all of the material needed for our existence is all within those within this one white dot. And all this material is brought to us, well, from dead stars that died a long time ago and brought to us here on Earth by lots of physics and chemistry. And with that, I'd like to end my talk and thank you for your attention.
Thank you very much, Dr. Van de Sande, and Dr. Sean Prosser is here to help us with Q&A. I have a question because I've done an astronomy certificate at UCL, and I remember one of the most fascinating things that they talked about was that molecules that form in space, because the temperatures are so low, those are things that we can't reproduce on Earth. So is that what you're doing in your theoretical studies? Because obviously, I'm assuming you can't reproduce them in the lab.
So in the theoretical models, you can make all of the molecules that you want, of course, because you can plug in whichever reaction you want, but you do still require laboratory experiments, because and then you run into the issue of forming these quite exotic molecules, such as C4H, for example. For that, you need a lot of expensive equipment, a very ultra-high vacuum pump, which doesn't even bring you close to 10,000 particles per cubic centimeter. Lots of lasers as well. But you can make most of these molecules just with a great expense. And some are also quite dangerous, like all the cyanide ones. Well, yeah, that will kill you quite quickly. So you can also resort to theoretical models, molecular dynamics, but that's only really useful for very small molecules, because otherwise it's computationally not feasible anymore. And then you will have to make some assumptions as well. So yeah, ideally you use lab results, which can be quite difficult for loads of reasons. And otherwise you can make some assumptions. As long as you know what you're assuming, it's okay-ish.
Thank you. That was really interesting. I had a couple of questions. My first one was, so you mentioned the AGB stars. One of the questions that I had is, once the dust escapes from the AGB star, you said that the molecules can be photodissociated, but are the dust grains themselves also photodissociated?
That's a great question.
Second question I have is, do we have any idea of, for a star of a given mass, how much dust it produces in this AGB phase?
Oh, right, yeah. Two great questions. So for your first question, all your molecules will be destroyed, but dust is quite stable. So it's it's very difficult to just destroy it with UV light. So the dust remains, but it will, of course, experience some changes as it moves through the ISM, like it experiences a shock wave, for example, and then it gets shattered into smaller pieces, but the dust remains. Small molecules will be photodissociated. So all this funky chemistry, well, it's all for nothing. And then, yeah, we do have some sense on how much dust they produce. Of course, it depends on your initial mass, but they produce several. Oh, no, I only have numbers in my head for like galaxies and stuff, but they produce several, might make a mistake here, but like 1/10 of a solar mass comes from the sun, for example. So it's quite efficient. They do produce a lot of dust. And if you look at all of the stellar dust that is being produced by a galaxy, then most of that dust comes from AGB stars. And then we're talking about like hundreds of solar masses of dust being formed. So yeah, but I'll look it up maybe.
Thank you for a very interesting lecture with lovely illustrations.
Thanks.
Maybe slightly off topic, Betelgeuse I believe, has been changing in brightness quite a bit recently.
Yes.
Does that suggest it's on its way to being supernova?
So that was one of the hypotheses, but in fact, one of my former colleagues at KU Leuven found out, well, through observations, of course, that it's because there's a large glob of dust that was being formed within the outflow. Also, massive stars have outflows, they're a bit different though. And this blob of dust sort of blocked the view of Betelgeuse. So it's not going supernova anytime soon. It was just a big blob of dust hiding it from our view, because these stars are also very convective. So that was what's going on. Either it's like one of the main theories are just convective motion or just dust formation, just shielding, well, hiding it from our view a bit. But yeah, not anytime soon. We'll have to wait a bit longer.
Okay, I have a question from our Zoom audience. Simon Street asks, what about dying stars back at the very early stages in life of the universe, and if they had very low metallicity?
It's a great question. So that's something that the James Webb Space Telescope is really helping us now and also confusing us a bit more. So you would expect in the early stages of galaxy that, well, the universe, aren't there many heavy elements yet, because not enough stars have died yet. So you would have less dust, but actually these early galaxies still form quite a lot of dust and quite efficiently so. So that's one of the more cosmological questions when it comes to dust formation, exactly how these early stars are able to produce so much dust as well. So yeah, it's a great question.
Okay, thank you, Simon. Pedro asks, what kind of evolution could be expected for white dwarf stars and neutron stars?
So for a neutron star, so it's end of life, right? After a while, your neutron star will lose. Well, for neutron stars, I'm not entirely, well, I don't know the details, but for white stars, I do know that they start to cool down. They don't have any source of energy anymore. They have quite a high temperature, but over time they will cool down and become so-called black dwarfs. Now, there's no black dwarfs exist yet, simply because the universe isn't old enough for black dwarfs, well, for white dwarfs to have cooled down and become a black dwarf. And I suppose that for a neutron star, it's a similar mechanism. So you sort of cool down and die a quiet death. Yeah.
We still have a good 8 minutes. If you have a question, please raise your hand and we'll pass you the mic. Yep.
Very futuristic. When the universe comes to an end, how will all this play out? Chemistry.
So I'm not a cosmologist, but yeah, I don't know. Well, when the universe ends, maybe if it all collapses all in one singular point, then we will just become hydrogen and helium again, I suppose, and everything will be melded together back in the like the primordial to Big Bang again. Well, I suppose that is what happened, but I don't know. I don't know. That's not my area of expertise at all. But yeah, it will all be for nothing, I suppose. Or for nothing. We might have as well have some fun along the way. Oh, right, yeah.
So Brian Cox was highlighting in his astronomy programs.
Oh, right, yeah, yeah. Yeah, he's more of a particle man. As a...
Is the dust continuously formed? Like, so the dust that was formed by the earlier stars, is that all the dust in the universe, or is it being like formed?
So the dust is experience lots of changes. So as it enters the ISM, it's probably shattered and then it's reformed again. But also once it enters a star-forming region, well, if it does becomes part of a star, it will die. Like that's more than UV photo. That's more than just UV radiation. You're really melting your dust and making it into a plasma. So the dust that we see floating around in space is sort of is more of a product of the entire evolution of the dust. So maybe you have some primordial stellar dust grains, but most of them will have been reformed and reprocessed throughout the life cycle of your galaxy.
So as well as the molecules that have been detected in the ISM, have we spotted basically every element on the periodic table?
Yes. Wait, I've got a slide. Haha. There we go. So almost everything has been, so this is a periodic table of elements, and the colors show you the different origins of each element. So you've got a Big Bang fusion, that's hydrogen and helium. You've got dying Loma stars, so AGB stars, that's a bunch of carbon and nitrogen, etc., etc. So they've all been detected in space, but you also spy these two gray guys, and that's because they're very unstable and they will have like broken apart. So their half-lives are quite low. And then in the periodic table in a chemistry lab, you also have many more over here, and they've got it's like 118 in Latin as a name, and after a while it does become named, and those have been formed in the laboratory. Perhaps you can form them in space, but then for a very, very short period of time. So for those, you really have to like smash things against each other in CERN, for example. But yeah, I think we've detected most, except for the very exotic ones.
Oh, fantastic. We got a bonus slide in the evening talk. That's excellent. Earlier in the day. I do have several questions online, so it might be the end of it because we only have about 4 minutes, but James from Zoom asks, what is your view of the likelihood of so-called quark stars, a Goldilocks option between neutron stars and black holes as the end of life for massive stars?
Well, that would be a very interesting way. So all these exotic stars, well, so quark stars, rather than like being formed of baryonic matter or like neutrons and whatever, made out of quarks. I don't know. To be honest, I don't know enough about that to give you an opinion. It would be cool if it existed, but so far it hasn't been detected yet. But yeah, let's keep looking for them. But yeah, I'm sorry, James, I don't know anything about that.
Your wonderful slide has started off a bunch of.
Oh no.
I'm going to get to a couple. AC asks a couple questions. One, what would you think would be the largest number of carbon atom molecules that might be detected beyond buckyballs? That is.
Well, I suppose, well, you can look at a carbon-rich dust grain. So that's a soot particle, which is basically just a bunch of carbon atoms stacked together. So that's a lot of carbon atoms, depending on the size of your dust grain.
They also ask, very heavy elements such as gold are believed to be formed by merging neutron stars. Is there any organic chemistry also generated during these events?
No, because it's a very energetic event, so loads of radiation, and that will kill off all of your molecules. Even if you could make any, they would die immediately.
Oh, very interesting
right,
question,
yeah.
yeah. And finally, Henry asks, overall, how much dust comes from sun-sized stars compared to the giant stars?
So if you look at just stellar dust that's being formed, like in the Milky Way, you find that supernovae produce about like 30% of all of it, and sun-like stars, so AGB stars, about 70%. So they are thought to produce the majority, but the ratio changes as more observations come. So sometimes supernovae dominate, sometimes AGB stars dominate, but it seems like it's, well, to me, it's AGB stars, but yeah.
There's another question here from Simon. I'm not sure. They just ask, how about lithium oxygen molecules or beryllium oxygen molecules, etc.? But they don't give much.
Oh, in these highly energetic events, there's going to be so much X-ray and gamma radiation that even if you were able to make them, you would photodissociate them, I think. So it's just too warm. Things don't want to be a molecule if it's too warm.
I mean, it's obviously a very Very, very interesting topic. And I thank you so much for traveling all the way
Oh,
from
thank you,
Netherlands
thank
to
you.
come be with us today, doing 2 talks here in London. The last chance to ask any more questions. We have 1 minute left. Oh, there we go.
Just chat. Running out of time. What's the heaviest element that's been?
The heaviest element that has been found in a compound. So for a molecule, yeah, so for these molecules, I think we'll have to cut it short at around aluminium, well, argon, so argon over there, argon with a hydrogen atom. That's one that I can think of. Iron oxide, sorry. I only know also iron oxides, titanium oxides have also been found around AGB stars. And yeah, I think iron oxide, but don't quote me too much. Yeah, but like definitely in this region, oxides.
Excellent. Well, thank you so much for your brilliant talk
Thank you,
and
thank you.
sharing all of this information with. Thank you. Thanks, Dr. Van de Sande, for being with us again.
No, thank you for coming. As we go for site and then